Hello again, welcome to Lecture 3. So before I get started, I have an announcement. If any of you are thinking of being a math major, we have a course, Math 130, that's Colloquium in Mathematics. It's a one-unit course. It's intended for math majors. In fact, it's required for math majors, so if you're going to be a math major, you'll need to take the course. And it's intended to just give you an overview about what the math major is all about. Sometimes people um, you know, they'll choose a math major based on calculus, but there are more areas of math than just calculus, and so you get a little bit exposed to what kind of courses are coming up ahead of you. I'll give you an idea as to whether or not this is something you really want to do, and if you're interested, then definitely this is math major is a good way to go. This is also therefore good for people who are not sure if they're going to major in math. This might very well help make that decision. In addition, we'll talk about things like, you know, things you can do with your math in your career and things like that, and maybe some fun areas of recreational mathematics as well. So anyway, that is next semester. It's offered every spring. It's required for math majors. So recommend taking that. All right, so let's get started. So last time we saw that the integral of f dot dr, okay, this line integral is independent of path when f is the gradient of a function. Okay, so this came out of the fundamental theorem of calculus for line integrals. When I say it's independent of path, that means it just it just depends on the start and end points. It doesn't depend on the actual path you take to get from one to the other. Now, this only works where f is the gradient of a function. What happens when f is not the gradient of the function? Well, then the fundamental theorem of calculus for line integrals does not help us there. We don't really know then what's going to happen with this line integral. And what we're going to see later on is that this independent of path is really only for gradients of functions. Okay. So a theme that's going to really occupy us for the rest of the semester, not every, there will be other themes as well, but one of the important themes is when is a vector field the gradient of a function? Okay. So here we got the equation, f is the gradient of a function. Okay. This is called conservative. If a vector field is the gradient of a function, we call it conservative. This is not a comment on the political beliefs of the vector field. This is just an homage to the famous conservation of energy. So it turns out that if your force field is conservative, so it's a gradient of a function, that relates to being able to show that energy is conserved. The book talks a little bit about this. I won't really get into it. I figured that you can learn about this in your physics classes, but this is a really key, important idea in physics, conservation of energy, and it all has to do with this being the gradient of a function. Okay, let's look at an example. Okay. Is this vector field x squared y comma x, this is the x component, this is the y component, is that equal to the gradient of a function? Okay. Now, in other words, we need to find a function g so that the partial derivative of g with respect to x, that goes here, is this, and partial derivative of g with respect to y is this one, x. Okay. So we're asking, is there a g so that that's true? Well, it might be a little hard to tell at first until you realize that actually, if g exists so that this is true, then we can take partial derivatives again. And in particular, we're interested in the partial derivative of this with respect to y and this with respect to x. Why is that? Well, then that's going to be our mixed partial derivatives, gxy and gyx. And we know that Clairaut's theorem says that gxy equals gyx. Okay, so if this was really gx and this was really gy, then I can take the partial derivative of this with respect to y, this x component with respect to y, and the partial derivative of this y component with respect to x, and those should be equal. Here we get x squared, partial derivative of this with respect to y is x squared, partial derivative of this with respect to x is 1. These are not the same function. X squared and 1 are not the same function. I mean, there are places where x squared and 1 happen to coincide, but as a function, these are not the same function. So no, it can't be that this is the gradient of a function. If it were, then we'd have a violation of Clairaut's theorem. Clairaut's theorem, by the way, also requires that these be continuous, but of course these are continuous. X squared and 1 are both continuous, so that's not a problem. All right, so what have we seen? This shows us that there is a test we can apply. If I want to know if a function is the gradient of a function, a vector field is the gradient of a function, all I need to do is take this this component and this component. Take the partial derivative of this x component with respect to y, the y component with respect to x, see if they're equal. So let's call this one p and this one q. Then for f to be conservative, the partial derivative of p with respect to y and the partial derivative of q with respect to x have to be equal. So this is an important criterion. If it's not, if py is not equal to qx, then we know that this is not conservative. So that's pretty straightforward. Well, what if py is equal to qx? Does that mean this is conservative? Well, hard to say at this point. Actually, this is something that we'll need another lecture to really address. Okay, so this is going to be a little while before we actually address this point. But I want this this question to be hanging in your heads for a while. So great, we have a condition that if this is not true, then we know it's not conservative. If it is true, then we're still not sure. All right, let's look at another example here. Here's a vector field. Okay, e to the y plus x squared is the x component. X e to the y plus y cubed is the y component. So that's p. This is q. I just picked out the x component and y component. Take the partial derivative of p with respect to y, partial derivative of q with respect to x, as I'm supposed to. So partial derivative of this with respect to y, that's e to the y, and x squared is constant. So partial derivative of that with respect to y is 0. Here, similarly, partial derivative with respect to x this time, the x becomes 1, the e to the y remains, plus 0. And we know that we see that we get e to the y in this case, e to the y in that case. These are equal. And so, yeah, this is looking encouraging anyway. At least this has not broken Clairaut's theorem. So there's some hope that this is really conservative. So let's try it. If this is going to be really conservative, that means this is going to be the gradient of a function. Okay. That's the question. Is it the gradient of a function? Call that function g. Then partial derivative of g with respect to x would have to equal this, and partial derivative of g with respect to y would have to equal that. So there we go. G sub x would now be this. G sub y is now that. Okay. The one step that, I don't know, I think most people, when faced with this, would eventually do something of the following type. If this is the partial derivative of g with respect to x, let's just integrate it. Okay, let's just find what g is. Okay, when we integrate here, remember in this equation, y is a constant. So I'm going to treat y as a constant and integrate it like this. And so e to the y is a constant, so I just multiply by x. And then integrate x squared is 1/3 x cubed. That's the integral, right? Hold on. Was there supposed to be a plus c here? Actually, sounds like there ought to be, but if you think about it a little bit more, you'll realize that something more subtle is going on here. You see, through this whole process, we treated y as a constant. So y's could be hanging out in this so-called constant. This is only a constant with respect to x. In other words, it could be a function of y. So there we go. I'm going to call that function of y h of y here. So instead of adding a constant, I'm adding a function of y. All right, so there we go. G of x comma y is equal to this. Now, of course, h of y is still unknown, so we're not out of the woods yet. But we got something here. Okay. Many students, when they see this, okay, their first instinct is, well, okay, this worked well when I integrate this with respect to x. Let's now integrate this with respect to y. You could do that. It's going to make later steps a little more confusing. So I'm going to recommend that you don't go that route and instead do something slightly different. Okay, that is, just take the partial derivative of this with respect to y and match it with this. Okay, it's easier, right? You don't have to integrate, you just have to take derivatives. So there we go. Take the partial derivative of this with respect to y. X e to the y derivative of that is x e to the y. Okay, remember, this is partial derivative with respect to y here. Plus, now this goes to 0. And then this is h prime of y. Remember, h is a function of y, so it's only a one variable function, so this is just a single derivative, an ordinary derivative, like you learned about in Calculus 1. All right, so we get this equals, and then this is what you get on the other side, x e to the y plus y cubed. So this is equal to this, x e to the y's cancel, and we end up with h prime of y is equal to y cubed. I should point out here that this is where the real danger was averted. There was no guarantee that this thing was only going to involve y. It could have involved x's. I mean, if this was something else, which it could have been, this is the first time we've used this, that had maybe some x's around, there could be x's hanging out here. Okay? But yet, this is supposed to be a function of y. And then we'd run into a contradiction. This is what did not happen. Okay, in this case, it just has y's in here. There's no x's. And so this is something we can easily solve. Okay. So in examples where the vector field is not conservative, this is where things might go awry. So I just copied these two lines from the previous slide here. This is g. This is h prime. Of course, I can just integrate it. There we go. It's 1/4 y to the 4th plus constant. Plug this into here, and there we go. We get this. There's your g. You can verify that the partial derivative of g with respect to x is what it's supposed to be, and partial derivative of g with respect to y is what it's supposed to be. Gradient of g is really the vector field, and that vector field, therefore, was conservative. There's a picture going behind this. I mean, that was pretty fun to do, and you'll have lots of practice to doing that. But that was all really symbolic, algebraic. I'd like sometimes to look at things in a different way, and I like pictures, so I'd like to show you the picture behind what was really happening there. Before we do that, I want to review what happens in one variable calculus. So this is what you did in Calculus 1. You may have not have used the language that I'm going to use. I'm making it a little bit more, highfalutin for you guys that have some experience with calculus. So given a function f of x, how can we find a function g of x so that g prime of x equals f of x? This is analogous to the situation we have where we want the gradient of g to be this vector field, a given vector field. So here's a function. You want something whose derivative is that function. And what we do is we use the fundamental theorem of calculus. Okay, this is the fundamental theorem of calculus. Okay, I'm using g here. I'm using t as my variable because I want to use x for something else. Okay. And I'm just going to choose a and my b appropriately. I'm going to choose a to be 0 and b to be x. By the way, if I choose a to be any other constant, this would work. 5 or whatever, pi, this would work. I'm using 0. Doesn't really matter. Okay. And then you have this equation. G of 0 here is this a constant. So I'm going to call it that, a constant. And then I'm going to solve for g of x. And you see you can add this constant to that side. G of x is now equal to the constant plus this integral here. Okay. Oh, along the way I said g prime is equal to f. That's the other thing that happened here. Okay. So there we go. This is the formula for g. This, by the way, demonstrates that in one variable, every function has an antiderivative. Every continuous function, anyway, has an antiderivative. Okay. All I need to do is put that in here, and this is going to give me, for every x, this is going to give me some number. Okay, and then just add this constant, and this is going to give you a number. So in other words, for every input, there's an output. That's what a function is. Okay. You might not be able to write it down. That e to the minus x squared example is a case where we might not be able to write it down, but this is something. Okay, it is a function. For every input, you have an output. The other thing that this shows is that the only ways you're going to get different kinds of answers to this question is by adding a constant. Okay, so this is something very specific, and this is adding some constant, and these are all of the different antiderivatives of your function. So, all right, so that was one variable calculus, fundamental theorem of calculus. Use this to find antiderivatives. Now, let's apply that to our situation, conservative vector fields, multivariable situation. So given a vector field p comma q, how can we find a function g so that the gradient of g is equal to p comma q? The first step that we did is we integrated. Oh, do that here. I integrated this. Okay, this is my p, this is my q, and I just integrated this with respect to x, assuming y is a constant, and I added a function of y. So I'd like to show you here what that looks like. So this is the integral of p. I'm going to integrate from 0 to x and add h of y. Okay. This is what this looks like. It's integral of p dx on this line segment here. Okay. This is at a particular point x comma y, put 2.1 comma 1.6, just at random, but for any point in the plane, you would have y be 1.6 or whatever it is, and this would be an integral where y is constant, so it's a horizontal line. And you're going to start off at some place. I'm going to start at 0. Of course, I could choose any constant here, but I'm choosing 0. Okay, and I'm going to take this integral of p dx. Okay. And then I'm going to add a constant, not really a constant, it's going to be something that depends on y, but from the point of view of this integral, it's a constant. If I have other integrals at other places, I would get different constants here, but that would only depend on y. That's why this is a function of y. That's what this picture is showing me. Okay. Now I'd like to look a little bit more closely as to what this is. And to do that, I have to just look at what's going to happen when x is equal to 0 here. So I'm going to plug in x equals 0. So this is going to completely go away. Integral from 0 to 0 is 0. And so g of 0 comma y is h of y. And I want the partial derivative of this with respect to y to equal q. And the way to do that is I integrate this way. Okay. And so I'm going to have h of y is this integral here from here to here plus a constant. And so I'm going to stick this into here, and I'm rearrange it a little bit. You got this integral plus a constant. I want you to notice something. This can be combined into a single integral. It's an integral of this along this curve plus an integral along this curve of this. Here's the thing. When I'm doing this part of the curve, y is changing, x is not. So dx is 0. So in this integral, this is going to be 0 here. I'm integrating q dy along this. That's giving me this. And then I've got this integral here. Here, dx has something, but dy is 0 because it's a horizontal line. Y is not changing. So this is going to be 0 on this. So integral of p dx plus q dy is going to be the right thing for here and for here, and that will give me these integrals. This is the integral of f dot dr, by the way. Remember that? So integral of f dot dr from along this curve, plus some constant, of course. Here's the thing. Once I have this, then the partial derivative of this function, this is now a formula for the function g. Once I have this, this will have the correct partial derivative with respect to x. Actually, it had that earlier, all the way back to here. The partial derivative of this with respect to x is just going to be p. Okay. The partial derivative with respect to y, though, who knows what that is? Here's the thing. I could do this whole thing, but do it the other way instead. Do it this way and then this way. And so here's the idea. H will only depend on y whenever this integral and this integral give you the same answer. If this is independent of path, that is, this integral and this integral have the same answer, then the partial derivative of this with respect to x and the partial derivative with respect to y are equal to what they ought to equal. Okay, the partial derivative of this with respect to x will be p. The partial derivative of this with respect to y is q. Because it's equal to this, you can see that the partial derivative of this with respect to x will be p, but we don't know what the partial derivative with respect to y is. Because it's equal to this, though, then the partial derivative with respect to y will be q. So then we've got all our bases covered, and this really is this does work. The gradient of this really is our vector field. And that means our vector field is conservative. Okay. So this independence of path, remember this is an integral of f dot dr here, is it's not just a random trivia that you can say about conservative vector fields. It's actually fundamental to the subject. Okay. So here we go. G of xy is equal to this formula, constant plus this integral of f dot dr. Here I say C is any path that goes from 0, 0 to x comma y. Again, I could have chosen any other point. I'm choosing 0, 0 to make things easy to think of, but I could put any point here instead. Constant point. C is going to be this path from 0, 0 to x, y. If I change this point, then of course this constant will change. Okay. And once I say that, you might say, well, don't you have to say which path? But if the integral is independent of path, then I don't. Choose any path. Choose a straight line. I don't know. Choose something really fun looking. Doesn't matter. It's independent of path. You're going to get the same answer. And then the gradient of G is equal to our vector field F. So this here is the theorem that I wanted to focus on right now. Okay. So that's what we just proved. Okay, when you have these line integrals are independent of path, f dot drs are independent of path, then this is true. And if this is true, then this is independent of path, as we saw last time. So there we go. This integral of f dot dr is independent of path. You can write it like this: p dx plus q dy is independent of path, either way. That implies that f is conservative. If you want p comma q, okay, is conservative. Is equal to the gradient of G. This and this are equivalent. Now, if this is true, then we can use the Clairaut trick. Q sub x must equal P sub y. Partial derivative of this with respect to x equals partial derivative of this with respect to y. And you might wonder, can we go backward? Again, that's going to take some time. I'm starting to develop the ideas. And by the end of next time, you should understand how this whole thing is set up. By the way, an equivalent formulation, I can ask, is this a total differential? So if you recall earlier, I had this, this is the x component, this is my p, this is my q. I had basically pi plus qj, but now I'm getting p dx plus q dy. If you recall, the total differential means when you take d of this, I'm going to take the partial derivative of this with respect to x dx plus the partial derivative of this with respect to y dy. And so this being the partial derivative with respect to x of this, and this being the partial derivative with respect to y of the same thing. This is basically the same question as is the earlier thing, the gradient of something. And indeed, we saw that this was the correct function. If you take d of this, we will get this. You might think that the vector field description is more visual. I think so too. But actually, this this way of thinking is actually pretty important in thermodynamics. So people were trying to define things like heat and things like that, temperature and energy and all kinds of things like that work. And one thing they realized was that we can talk about heat kind of flowing from one area to another area. Okay, and as they wrote down what's happening, well, each little step of some kind of mechanical process or something or other, as pistons move or as chemicals get mixed or something, a certain amount of heat gets transferred. Okay, and if you add it all up, um, you get an integral. Okay? And the original idea was that heat, there was something called um, caloric, certain kind of substance called heat. Each thing had a certain amount of heat, and heat flowed from one thing to another when you had too much of one in one area, not enough in another, and it would just move there. And what it turns out is actually, when you actually look at what heat is, total amount of heat that's transferred, it's this integral of these small little changes in things like volume or pressure or things like this, temperature. And if you write this out, you'll find that that is not a total differential. And basically, it disproved the caloric theory of heat. It showed that heat was not such a simple idea as just a certain amount of stuff that's it's not like um, you know um, my table has a certain amount of heat, and the air next to it has another amount of heat. It doesn't work that way. So anyway, I don't want to get too far into thermodynamics here. I just wanted to point out that this kind of question is key in thermodynamics. So in thermodynamics, they're always trying to ask, is this a total differential? Or sometimes they ask, instead of total, they use the word exact. It means the same thing. They found out that certain things like heat and work are not total differentials. Other things are. There is really such a thing as energy that really is comes out of, but there are other ones that are maybe not so obvious, one called entropy and things like that. Anyway, that's you'll learn about that in thermodynamics, and I want to just point it out to you here so that you see that that's going to play a role in the later classes. All right, I wanted to mention that this all works in 3 dimensions. Okay, there's not much to really say here, but I wanted to point out a couple of things here and there. Here's the 3-dimensional vector field. It depends on x, y, and z, and it has x component, a y component, and a z component. I'm going to call that p, q, and r here. Okay, p, q, and r. Remember, Clairaut's theorem in 3 dimensions is more complicated because this is supposed to be the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. And if I want to find mixed partials, there's more than one way to do it. They can have x and y, or x and z and y and z. So I need this one. This is the one I used before. Py equals qx. Partial derivative of this with respect to y and partial derivative of this with respect to x have to match. But also, the partial derivative of p with respect to z and the partial derivative of r with respect to x have to match. That's the other mixed partial with x and z. And similarly with these, with y and z. So the partial derivative of q with respect to z, partial derivative of r with respect to y, those should match. So we've got 3 things to consider. I've actually chosen one here where actually all of these things really are true. Go ahead and check them if you want. In other words, I'm hoping that g sub x can be equal to that, g sub y is equal to that, g sub z is equal to that. And the same trick works. Okay, it's a little bit longer, of course. Your g, just take the integral of this with respect to x, and there we go. This, though, is a function of y and z. Okay, so remember, when I take the partial derivative with respect to x, both y and z are constant. So that's why I need this function to be a function of y and z. This is the point at which it's good to do things the way I described it. Take the partial derivative of this with respect to y. Don't just integrate these things. Take the partial derivative of this with respect to y, and you will see this x squared, this goes away, this goes away, plus the partial derivative of h with respect to y should equal this thing here. Okay, x squareds cancel, and you get hy is equal to negative y plus natural log of z. Okay, so integrate this with respect to y, and we get this here. Okay, and this is a function of z. Take this, plug it back in here. This is now my new formula for g. And so notice g at first was just a function of x, y, and z. Now it's a function of x, y, and z. It has this part plus a function of y and z. When I do this now, it's all of this plus a function of just z. So I figured out the dependence on x, then I figured out the dependence on x and y, and now this is remaining. Take the partial derivative of g with respect to z, get the derivative of j here, is equal to this, and certain things cancel, and we're left with j prime is equal to z. So we integrate j, we get this, 1/2 z squared plus constant. Plug this back into here, and there we go. This is now g. Okay. I'm trying to show you how to organize it. It's possible to just go by your wits and just kind of wander around, but it's also easy to get lost. And so I'm putting it in this order so that you can, you can find your way through the forest, basically. Basically, I'm always looking at G. And when I do something temporarily here, I take that information and plug it back into G. I'm always taking partial derivative of G with respect to different things and matching it with these. Okay, and as soon as I find more information, I plug it back into G to expand this formula. Okay, so that's how I'm doing it here. All right, so there's something else that I wanted to mention. There is something else that is equivalent to the independence of path criterion. This is something pretty cool. So let's say it's independent of path. That means for every start and end, if you take this path and this path, you get the same answer. Of course, I can move this to the other side of the equation. This says the same thing, right? This integral of C1 minus integral of C on C2 is 0. This is the same thing as this. So saying it's independent of path is saying for every C1 and C2 that start and end here, okay, start here and end here, that this is true. And now I'm going to do something funny. I'm going to think about the path that's C2 but going backward. Okay, C1 I'm going to keep going this way, but C2 I'm going to turn backward. I'm going to call that negative C2. Negative C2, I mean, it's kind of a funny thing. I mean, C2 is not a number, right? So what does negative it mean? It just means take the curve, C2, and just go backward. Okay. And so I'm just calling it negative C2 here. And when I do that, the integral of f dot dr changes sign. So remember, this was a minus sign here. This will change sign when I change C2's sign, orientation. And so instead of minus, this will be plus. Okay. And the last thing I need to do is just recognize that this followed by this can be put into a single integral going over this entire loop. Okay, so if I just think of C1 followed by backward C2, that is a loop. I just have to forget that this is an endpoint. Call this C. And now the integral on C is now 0. So you might want to go back and review the past couple slides here until you really get what's happening. The point is, this is equivalent to this, which is equivalent to this. So this and this sharing the same answer is the same thing as this loop having integral being 0. You'll notice I put a little circle on here, a little loop here. Okay, this is traditional whenever your path starts and ends at the same place. In other words, it's a loop. Okay, this doesn't change how you compute it. You just compute it like you would any line integral. I just put a little loop there to remind you that C is a loop. It starts and ends at the same place. So here's the thing. This is equivalent to independence of path. If every loop had integral of f dot dr equaling 0, then this one plus that would be 0. And then this one minus this would be 0. In other words, this and this would have the same answer. And so that would be independent of path. So this is kind of a cool way of rephrasing independence of path. Just the integral around any loop of f dot dr is 0. So here's an example where I've chosen this vector field -y comma x. We saw this earlier in the first day of vector fields. It swirls around like this. Okay, and I've chosen this path C to go around in this solid circle here. And you'll notice that as I go along, integral of f dot dr is always positive. It's always going along the vector field. So this arrow is supposed to go that way. So as I go along this, okay, I'm adding up a bunch of things that are positive. So I'm going to end up with something positive. This is not going to be 0. Okay, so therefore this is not independent of path. So this vector field is not conservative. One way of thinking about this is you kind of wander around here. I climb and climb and climb, and let's say this is the gradient of a function. Then as I go here, I'm climbing and climbing and climbing in value, and when I come back, you know, I'm supposed to be at the same place, but somehow my value of my function is different now. It's now bigger, so that's a contradiction. So to summarize, we've got now all these different conditions. The integral on any loop being of f dot dr being 0 for all closed loops. This integral being independent of path only depends on the start and end point. Those are equivalent. This is also equivalent to f being conservative. And if this is true, then qx equals py. That's Clairaut's thing. If this is true, again, we're still waiting to see, does that mean any of this is going to be true? We're still uncertain about all of that. Okay. So, one thing to note, by the way, this is the thing we're actually interested in. Is it conservative? This is easy to check. Okay. These other conditions, those are terrible conditions to check. I mean, I have to choose look at all the paths. How many paths are there? I mean, infinitely many. I mean, it's worse than infinitely many. It's like unthinkably infinitely many, because I have to kind of think of all the possible paths. Same with these. I mean, this at least we're limiting it down to not in paths in general, but closed loops. But that's not much of a limitation. I mean, there's still lots of loops out there. It's kind of hard to think of them all. Okay. So it sounds at first that these, I mean, how could you possibly use this stuff? This one, yeah, definitely you could use that, right? Just take the partial derivative of q with respect to x, partial derivative of p with respect to y. See if they're equal. That's great. These, hard to use. Actually, the way we're going to show that this relates to all of this going backward is through these here. Okay. We're going to be rescued by a theorem, and that's 13.4. It's called Green's theorem. So next time, we're going to talk about Green's theorem. Looks like this. Okay. And here we get qx minus py. If qx equals py, then this is going to be 0. Okay. And this is an integral of p dx plus q dy. This is around a closed loop. And I haven't said what this is, but if that's 0, then that certainly helps with this criterion here. So that's next time, Green's theorem, and we'll talk to you about that next time.